Listen closely. At 7:14 a.m. on June 30th, 1908, a hard blue-white glare sliced across the Siberian sky. A few seconds later, the air itself hit back. A shock front rolled over the taiga near the Podkamenia Tunguska River and folded the forest like grass. Trees snapped, herds dropped, windows shattered hundreds of kilometers away. Seismographs in Europe twitched. Barometers traced pressure waves circling the globe. That single morning, minute left a fingerprint that lasted for days. People on the ground felt heat like an oven door thrown open. Campers saw a fireball rise, bloom, and fade to a column of light. A trader was blasted from his chair and blacked out. Far from Russia, the night sky turned strangely bright. Newspapers in London joked you could read outside at midnight. Photographs taken on those nights show a pale, milky haze. Earth had been hit by something big, but when investigators finally reached the site, there was no crater. For almost 20 years, the story lived as rumor. Russia had a revolution, a civil war, and no easy rail line into that deep interior. In the late 1920s, a hard-driving meteorite researcher named Leonid Kulik mounted an expedition. He hired Evenki guides, slogged through bog, swarms, and winter ice, and mapped what he found: more than 2,000 square kilometers of flattened forest. The pattern wasn't a neat circle. From above, it looked like a butterfly, two lobes fanning out from a central axis. Kulik expected a classic impact: a large bowl in the ground and a heavy mass buried under peat. He found neither. He dug test pits. He measured the lean of scorched trunks and the directions they fell. He brought divers to probe ponds. He returned in winter so he could cross the swamps when they froze. Still nothing. No iron, no hole, no obvious meteorite. The missing crater turned confusion into legend. If not a crater, what kind of blow can crush 80 million trees? Start with the simple physics. Space is full of small rocky bodies, asteroids, many only tens of meters wide and dark as charcoal. When a roughly 50-meter stony body slams into the atmosphere at tens of kilometers per second, it meets air that behaves like a wall. Pressure spikes. The rock superheats, fractures, and begins to fail. As it breaks apart, its surface area skyrockets. The shock wave in the air grows fast and violent. Energy meant for the ground is dumped into the sky. Instead, that is an airburst. No classic crater, no giant chunk buried in the soil. The trees at Tunguska tell exactly that story. Right under the line of the blast, many trunks were stripped of branches, yet still stood, poles with no crowns, because the downward gust pressed them straight. Farther out, the horizontal wind flattened the forest radially, laying the trees like straw around a campfire. The butterfly pattern fits a shallow incoming path, likely from the east or southeast, with the shock front curving down to the ground. How big was the blow? Models differ, but most estimates land between 5 and 15 megatons of TNT equivalent, with many clustering near 10 to 12. That's hundreds of times the Hiroshima bomb, big enough to flatten a forest and light, dry bark, but not the kind of event that must carve a hole if the energy couples into air 5 to 10 kilometers up. The air took the hit and delivered it to the trees. If that feels abstract, remember Chelyabinsk. On February 15, 2013, a stony meteoroid about 20 meters wide exploded over a Russian city. Dash cams caught the flash, the smoke trail, and then, minutes later, the shock that blew out thousands of windows and sent more than 1,000 people to clinics with cuts and bruises. No crater. The same basic story in smaller form. A space rock broke under aerodynamic load, and its energy turned into light and pressure in the sky. Chelyabinsk is Tunguska with cameras rolling and the scale turned down. So why did mystery cling to Tunguska for so long? Because the first expeditions went looking for a hole and a rock. Because the site is brutal to reach. And because wild alternatives are fun to print. Over the years, people have proposed a mini black hole punching through Earth, a blob of antimatter annihilating midair, a clean vaporizing comet, even a beam from Nikola Tesla's Wardenclyffe Tower. These are colorful. They fail once you ask for evidence that matches the full set of facts. What does the evidence say? In peat layers that grew in 1908, scientists found tiny spherules rich in nickel and iron and grains with elevated iridium, chemical signatures consistent with meteoritic dust. Tree rings show a stress year and changes you'd expect if heat and shock stripped needles and scorched bark. Eyewitnesses reported a bright trail in the sky and a rising column, exactly what a high-altitude fireball and expanding smoke plume look like. Barographs recorded pressure waves that wrapped the planet. Put those pieces together, and the picture is consistent. A stony asteroid came in fast, failed under load, and exploded in the air. One claim refuses to die: Lake Cheko, a small lake a few kilometers from ground zero. Some argue it's a late impact crater formed by a surviving fragment, but cores pulled from the lake bed indicate sediments older than 1908, and the shape looks like a river basin scoured by water and ice, not a fresh puncture. The simplest reading still works best. No large fragment reached the ground at speed. The atmosphere absorbed the blow. The best modern models treat the incoming body as a weak, fractured object. As dynamic pressure rose, it pancaked, broke apart, and dumped energy into a huge, expanding shock. That shock, shaped by the shallow entry, curved down and hammered the forest. Heat singed bark and ignited patches of brush. The main destruction came from pressure and wind. That explains the standing poles near the center, the radial tree fall farther out, the butterfly footprint, and the missing crater. Kulik never saw that full physics story anchored by later data and models, but his fieldwork made it possible. He measured directions, angles, and burn marks instead of forcing the site to fit a favorite idea. Later teams added magnetometer sweeps, aerial photos, satellite passes, and precise mapping of toppled trunks. Piece by piece, a messy human record became a clean physical narrative. A small asteroid entered at a shallow angle and burst in the air with megaton scale energy. There's a practical lesson. Tunguska was remote. It killed wildlife, erased forest, and startled people, but it didn't hit a city. Move the same airburst over an urban area, and you have mass injuries from glass and debris, plus fires and building failures along the shock's path. Chelyabinsk, at a fraction of Tunguska's energy, filled hospitals fast. We avoid catastrophe partly by odds, and partly by getting serious about the sky. That brings us to prevention. Survey near-Earth objects in the tens to hundreds of meters range. Track them long enough to predict future paths. If one is on a risky course, nudge it years in advance. A change of a few millimeters per second today becomes thousands of kilometers of missed distance later. Kinetic impact tests show the basic steering works. Wide-field telescopes and planned space-based surveys are expanding the catalog. The risk is real, but the fix is straightforward if we act early. Make the physics concrete. A 50-meter stony asteroid might mass a few 100,000 tons. At 20 kilometers per second, the kinetic energy is on the order of 10 megatons. Most of that releases between 10 and 5 kilometers altitude when the body rips apart and decelerates violently. The bright phase lasts seconds. The shock arrives after, strong enough to knock people down and implode structures that face it. That delay tricked many Chelyabinsk viewers. They saw light, walked to windows, then met the wave. Why did Europe see bright nights after Tunguska? Tiny particles lofted into the high atmosphere scatter sunlight long after local sunset, making luminous night clouds and odd twilight. Reports from Scotland to Russia describe pearly veils and a soft, extended glow. The planet wore the signature for days. Instruments traced the pressure ring for hours. The forest still shows the geometry more than a century later. Respect the human thread here. Evenki guides led Kulik's team through harsh ground. They had names for features and stories about the blast. Kulik listened, mapped, and came back with better tools. That is how you do field science when the site is hostile and the facts are loud. Move, measure, return, and check. That rhythm turned witness talk into a usable map. Comet or asteroid? Comets are ices laced with dust. Asteroids are rock and metal. An icy nucleus could, in theory, vaporize to nothing and leave few traces. But the chemistry in the peat, the intensity of the air shock, and the altitude of the burst point toward a stony body. You don't need iron to make a disaster. You need mass, speed, and air that pushes back like a wall. Tunguska also shows how gaps breed myths. For decades, the missing crater invited fantasies. Some were playful, some were earnest. The cure wasn't a single clever idea. The cure was accumulation, metal-rich spherules and peat, tree-ring chemistry shifts, vectors of fallen trunks, distant barograph traces, and finally a modern airburst seen on 100 cameras that behaved by the same rules. A good story doesn't die when evidence arrives. It gets better because it becomes true. Visit the region today, and you walk a classroom. Young trees grow through an old disaster. Scars mark trunks that somehow stayed upright under the central downdraft. Trails trace the lobes of the butterfly footprint. The land says, this is what the sky can do. Here is how to read the ground when it happens. Lock the timeline. June 30th, 1908. Flash, heat, shock, and a pressure ring that circled the Earth. 1927. 1930s. Kulik's expeditions. The first systematic mapping. The careful, frustrating search for a crater that did not exist. Late 20th century. Geochemical testing, aerial surveys, and computer models that turned sketches into fits. 2013. Chelyabinsk, same physics, smaller scale, modern sensors. Today, hazard surveys, kinetic impact demos, and practical plans. Here's the clean conclusion. Tunguska was almost certainly a small, stony asteroid on a shallow path that exploded in the atmosphere and released roughly 10 megatons of energy 5 to 10 kilometers up. No crater formed because the energy coupled to air, not ground. The shock flattened the forest. High altitude, dust brightened nights. Instruments worldwide rang. The mystery persisted because the site was remote and expectations were wrong. Once the right question was asked, what happens when the air does the damage? The pieces snapped into place. There is no supernatural twist hiding in the taiga. There is a warning and a plan. The warning, small space rocks are common, and airbursts are part of Earth's natural hazard list. The plan, find them early and nudge the dangerous ones while nudges still work. That is what science is for. Turn fear into schedules, replace folklore with maps, and buy time to choose well. Stand under a clear night and look east. Somewhere out there is another Tunguska class, rock minding its own orbit. It does not hate us. It does not know we exist. Our job is simple and adult. Notice, calculate, and nudge. Tunguska took a forest and left us a memory. Keep the memory and skip the next forest.